better in case we have a large number of variables. And how can we collect this number of variables? We discussed the paper by Stockton and Watson, and then I told you that a lot of researchers try to use the same data or try to reconstruct the same data set of Stockton and Watson for the US, and there have been inconsistencies. And that's the reason why the Federal Reserve Bank of St. Louis, they decided to create a version, a lighter, I have to say, version of the Stockton Watson data set. And again, the idea is the same. We have variable categories, and inside each category we have specific variables: real personal income, industrial production, general index, industrial production, only the final products and supplies, only the final products, only consumer goods, only business equipment, and so on. So the main aggregate and all the sub-aggregates as individual variables. You have another category about the labor market, so not just unemployment, but as you can see here it says labor force, employment, unemployment rate, civilians unemployed, which have been unemployed for less than 5 weeks, from 5 to 14 weeks. So any kind of variable which exists, which is actually maintained and regularly maintained and exists for the US and has to do with production or labor or prices, as you can see here, or housing. So they have the categories, and any variable which is maintained, it's clear, it's seasonally adjusted, and so on, they include it in this data set. And therefore, now the idea is that we don't know which of these variables are going to be useful for estimation, forecasting, whatever you like. And the idea is that let's try to have a data set as big as possible, a number of variables, as many as possible. But all these variables, you have to be careful that they have to be maintained. So we don't want to include variables which are obsolete. We don't want to include variables which are discontinuous. So we need to have variables which provide data every month or every week, or the frequency you have, usually weekly and monthly. And once you have that, you organize them in categories, and for every variable, you have to go manually, okay? Still you have to go manually and think about it. So you're not a data analyst, you're an economist, and you have to say, I have industrial production. Okay, this is seasonally adjusted. Good. But how can I transform this to stationarity in a way that makes sense for economics? A statistician or a data analyst might say, take the first difference. It will work. It will make your variable stationary. But from an economics perspective, the first difference in industrial production is not something meaningful. However, if you take the log growth, right, this will show to you the economic growth. So this will be a proxy for economic growth. Therefore, it says here T code, transformation code. And here you have number 5. And if you go back to the legend, number 5 is the delta, so the first difference of the logarithm of your variable x or whatever variable you have, right? And this, unfortunately, you have to do it manually. So you have to collect your variables and you have to go variable by variable and think about them and say, industrial production, it measures growth. So let's take the log growth. Unemployment rate, right? It is expressed in percentage, it says. So if you look here, it says civilian unemployment rate. And this variable says to you, in October, the unemployment rate was 2.3%. So therefore, it doesn't make sense, economic sense, to simply take this variable and transform it to stationarity by taking the log growth, because you will be creating the percentage of a percentage rate. Therefore, as you can see here, it has the number 2 in front. And if you go back, you will see that number 2 is just the first difference. So once you have the rate, you simply take the first difference of the rate. Okay? And this is the idea. Usually the rule says something like, if you want some sort of feedback on that, if you have variables which are expressed in percentages, like unemployment rate, like bond yields, interest rates, right? you take the first difference. If you have surveys that are expressed in balances and you say, for example, what do you think will happen in the next 3 months in inflation? Positive or negative? And the balance is the first difference, is the difference of these two things. Then again, in that case, you take the first difference. If the variable you have is about production, or money, so if it is measured in pounds, in currencies, then you take the log growth. Or if you have an index, industrial production index, consumer price index, retail price index. So every time you hear index, or every time your variable is measured in currencies, like the GDP is 1 billion, and so on, you take the log growth. The rest are a bit less, let's say, frequently used, the rest of these transformations here. Have a look at this dataset. It's easily to find on the web. If you simply Google FredMD, you can find the latest version. This has been a dataset which has been maintained by the Federal Reserve Bank of St. Louis for the US. Okay? Now, in this module, we're going to do something simpler. Why? Because we want to have this kind of code that collects European data which is freely provided by Eurostat. So here we're going to do a snapshot of that dataset. We're not going to have 150 variables, we're going to have about 44 variables. But everything we're going to do today and next week, every line we write in R, every discussion we make for these 44 variables, the exact same discussion, the exact same code, the exact same commands can be used if you have 44 or 400 or 4,000 variables. Okay? The exact same packages, the exact same functions. And here we're going to have, we want to collect these variables. Production in industry, Euro Area 19 trade, production in construction, unemployment rate, money market, this is what, the 3-month yield, the 10-year yield, exchange rates, the 10-year minus 3-month treasury spread for the European country we are interested in. And here, these are the hard variables we call, which measure activity, real economic, let's say, activity. And here you have the soft variables, which are mainly surveys / expectations, okay? And if you can see here, on that side, this is, let's say, my incarnation, my idea for creating a sort of dataset like that. And this, the code will go on Eurostat. These are the variables from the Eurostat website if you want to have more look. And here I say transf, which means transformation. And I say, if you want to make variable with a label HD1, which is the production in industry, so industrial production, if you want to make variable HD1 stationary, take d log, so the difference of the logarithm. If you want to make variable HD5 stationary, which is the unemployment rate, as you can see here, then don't take the d log, take just d, so just the first difference. So in my case, I have d log, the difference of the logarithm. I have d, the first difference. I have na, which means don't take anything, don't do anything, it is stationary by itself. And here you can see for all these surveys, or almost all the surveys, you have d, first difference. Okay? And just because the description is a bit long, it says, for example, let me find a long one, general economic situation over the last 12 months from a consumer side. General economic situation over the next 12 months, consumer side. So we have this kind of long descriptions. Therefore, to give a variable name, I have this label on the far right end. So I call HD1, HD2, HD3, HD10, and then SD1, SD2, all the way to SD35. Okay? So these are our variables. Let's now download these variables. Last week, I have it here. I showed you that there is a code. This is the code. Last week it crashed, but I fixed it. And in this code, you have to install and then load the library Eurostat, which is the library which connects are with the Eurostat website, so you don't have to download things manually. Library Lubridate, which deals with dates. This is not needed, but anyway, we're not using this in the code. And Library Zoo to deal with NA approximation later on. Now, the code has been tested for Belgium, Germany, Greece, Spain, France, Italy, Netherlands, Luxembourg. For Ireland, I tried at home and there is a problem with an Irish time series, so it doesn't really work. Let's use France, okay? So you simply come here and you put the Eurostat ticker for the country. FR for France, DE for Germany, ES for Spain, and so on. I will use France and nothing else. You simply run the whole code. So Control Alt and run. And this code, if you want to look at it, goes here and says get Eurostat STS INPR M. So if you look at this file here, it says go to the Eurostat website and download this data, exactly the label we have here. And once you have that, then we specify we want to be seasonally and calendar adjusted. We want to be the production side. So these are specific settings for each variable. Nothing for you to worry about. I'm just explaining what you have to worry about in case you want to get data from Eurostat. At least this kind of data set from Eurostat. Just put the correct country code here and nothing else. Run the whole file and everything will follow. Let's see. It will take some time, I think, not long. So this code will download, once it finishes, will create an RData file. So it goes on Eurostat website, downloads all data, and then of course we don't want to press this button and wait every time we want to write the code. So it's wiser if we simply collect the data and save it in an R file. And that's what the code will do. So in the very end, which is here, the code goes and saves all this data in a file called step 1, data, your country code. So in my case will be FR. If you change the country, will be another ticker here, .rdata. So let's wait a bit more and see the data file. Don't worry about the red font here. These are just warnings that right now the package reads data from Eurostat from blah blah blah. We read this kind of information. It won't take long now. Now, once we have the data, which is not ready yet, what is the next step? So what are the things we discussed in the past 2 weeks? We have to go variable by variable and say, variable number 1, what it is? HD1. Okay? So take this variable. Check if it is seasonally adjusted. I know that our code, for example here, specifically says, if you look at the code lines, for variable 1, for example, it says S adds, so seasonally adjustment, to be seasonally and calendar adjusted. So from our side, we take all the necessary actions to make sure that what we are going to collect will be a seasonally and calendar adjusted data. But of course, in practice, people make mistakes. So perhaps when we write this, we make this mistake, which is just seasonally adjusted, or we make this mistake, or we make this mistake, not seasonally adjusted, right? So let's say we made a mistake, or let's say that Eurostat, in the place where they uploaded data, under the label seasonally and calendar adjusted, by mistake, they messed it up and they uploaded the not seasonally adjusted data. So we have to make sure that our code identifies that. So we have to go variable by variable and say, variable number 1, check if it is seasonal. If it is as it's supposed to be, continue. If it is not, make it seasonal yourself. How? For example, using the STL decomposition we discussed 2 weeks ago, or last week, or 2 weeks ago. The next step, make it stationary. How? By using this transformation we have here, log difference. Third step, once you have something which is seasonally adjusted and stationary, check for outliers, right? So everything we discussed last week, we wrote a specific code about one single variable, and now we have to repeat the same thing, not for one variable, but for 1, 2, 3, 4, 5, all those variables here. Code finished, okay, it says now done, and if you go to your directory here, you will see that this file now has been created. Step 1, underscore data underscore fr. So here we have all the variables for France. This is the first step. So this is when we just collected the data. This is still unchecked, still not stationary. So we go to step number 2, which says data cleaning. And if you go here, step number 2, okay, now we say, what is the file that you have your data? And we have step 1 data, fr in our case. What is the country you use? Fr again, and that's it. Nothing else you have to change. And this code will go and say, what is the choice of your rule of thumb, of your outliers? Do you want this to be the rule of thumb, or do you want this to be the Chen and Liu 1993? It's entirely up to you. So the code will do both. I will choose the first one, which is simpler, the one which is k as this away from the median. And in that case, I want this to be the median, and I want this to be 3 as this away. So these are the options you can play around with. There is one more option here, the significance level, and this is mainly for stationarity. We say, let's try to make a variable stationary. How? You take industrial production, take the log growth, but are you sure that this is stationary? So do a unit root and check if at 10% level you reject the unit root hypothesis, the null hypothesis. So all these things are just steps. Here we put transformations, 0 no change, 1 then growth rate, 2 the first difference, and these are for every variable we have. And then we say, you go here, you check seasonality. Okay, so up to this point, if I load this data, you don't have to change anything. I load this, does it work? Yes. So I load that, and then here I say, check if your data is seasonally. I run it and says, seasonality is found and fixed, 0 for your hard data, because the data you downloaded is correctly seasonal. For the soft data, didn't come back. I guess it's the same thing. I think so. Sorry, here. So DM2, hold on, here. So for the hard data, no seasonalities. For the soft data, seasonality is found and fixed 1. So somewhere here, somewhere in these files, in these variables, there is one variable which seems to be seasonal, and I failed to find that. And the code automatically found this and fixed it, as you can see here. And by this step, we have variables which for sure are seasonally adjusted. In this step, we make them stationary. Go and go. Once we have them to be stationary, we have to check, are they stationary? So these lines check that. Non-stationarity is found and fixed 0, so what you have is correct for hard data and soft data. So we have that, and the rest, here we have the outliers. Let's check for the hard data. Outliers found and fixed in 10 variables, so all of them, and here 33. I guess it's the COVID case. And now we simply save this file. And that's it, end of story. Now in the directory, we have another file, step 2 data fr, and this is now the clean file we want to use. So I copy it from here, I paste it here, and now we say we are here. This is week number 4. Load the clean data from Eurostat. So we go load, and what is the data file we want to load? This. Run, and here we have the objects. We care for the SDMs, stationary. Put all HD and SD together. So data to be SDM2, SDM3. So here I have just a single object, and here you can see your data. HD1, HD2, HD3, HD4, all the way to SD35. Okay? If you scroll down now, you will see that there are some NAs in the bottom 2 or 3 lines, which means that these variables, the data for these variables, has not been officially announced yet, and this is a problem we have for many economic variables, like production, like construction, so on. For now, we'll not discuss what happens if you have NAs at the bottom, but for now, we will remove the NAs from the bottom rows. So data to be NA omit data. That's it. So now we have this kind of data set. Do you want to export this in Excel? So do you want to, I don't know, have a look at this data file in Excel? Feel free to do it. Data out CSV, which is here. This looks exactly like a data set that in other case you would have downloaded from Bloomberg, and you would have, or any other provider, and you would have put variable by variable next to each other in correct dates. Okay, so we have data from 2004 all the way to 2024, I think, August 2024. Okay, and remember that these variables, the values you see here, are variables which are seasonally adjusted, stationary, outliers free, ready to be used. Do we agree? So everything about this data is what we have discussed in the past 2 weeks, but just done in an automated way, instead of you having to go variable by variable. Now, out of this data set, let's use this as our Y, the industrial production. And let's use everything else as our X. Okay? So Y is going to be the industrial production, HD1. And if you look at the legend here, HD1 is production industry. So let's use this as our target variable, which is the closest thing we can have to GDP growth in monthly frequency. And everything else, let's use it as an X. So I close this file, and here we say split your data Y to be data column 1 and X to be data all columns but 1. Okay, so -1. If you do -1 here, it means take all the columns apart from the first one. And that's it. We have Y and we have X. Okay? We have 44 variables in our X. And now the question is, very good, we have our Y, we have our X's. Which of these X's are useful? So how can we use this kind of variables? And somebody now will say, it's easy, do a regression. So do something like this. LM Y tilde X. What we learned in our first module, right? And then summary out. And here it is. You have your alpha hat, and then Vita 1 using the first x, Vita 2, Vita 3 and so on. And you have your alpha hat, Vita 1 hat, Vita 2 hat and the p-values. And you have here some stars indicating which are statistically significant and which are not. Do you agree? Well, yes and no. Why? The idea of using a linear regression is and will always be at the heart of econometrics, of this type of econometrics anyway. Okay? So using a linear model that simply attempts to find the relationships between a y and one or more x's in this very, very simple way by minimizing the squared residual, the squared error, is the simplest, the most robust, and will always be your preferred method in case you follow this line of research. However, there will be some problems in the way you analyze data. Here, we have a problem of, even though the estimation works, and we have no problems, and we can get values, and we can get p-values, we can get confidence intervals and so on, you can check your errors and so on, right? Your residuals and so on. You have a problem of interpretability, in the sense SD31, for example, has a p-value of 0.1066, which is just on the boundary of significance, which means that if you simply drop some observations or add some new, this variable, this coefficient, might also be significant. Or here, the 0.13, it's also very close to 0.1, right? So perhaps if you drop 2004 or 2005 as years of observations, perhaps this becomes significant. And therefore, let's have a look at another one. And here, SD15, 0.106277. And what else? I guess these are some very nice examples. And the question now becomes, are we going to be that strict on the significance? Usually you know and you say, if the p-value is less than 0.05, then at 5% I reject. If the p-value is less than 0.1, then at 10% I reject. Do you agree? But here you see some numbers which, technically speaking, are slightly, but marginally above the 0.1. One number here, another number here, another number here. So what do you do with these variables? Do you include them or not include them? Do you think that they are useful or not? And there is no answer. Okay? So the OLS in this stage does not really provide you an answer, a clear-cut answer on what you do with that. You have to be subjective. You have to go and say, well, I have to look at the p-values and I have to say, come on, this is a 0.13. Let's include that variable. Let's make it a favor and include SD33. But econometrics is not about making favor to variables, right? You need the data to come back and speak to you. So, one problem with OLS in this setup with many, many variables is interpretability. Another problem, which is not the case here because we have monthly data, another problem is when you have a larger number of variables than the number of time series. So here I say, as our data is, which is monthly, and we have a lot of time series info, technically our estimation will work, but we have the problem of interpretability as discussed in the lecture, in case you will go back and use this code. Okay? Then, another problem might arise in case you are in a setup where the number of time series observations, usually denoted by the letter capital T, or N, usually by T, is smaller than the number of variables, usually denoted by N or K. Okay? So, in the previous example, our T, the time series, is much larger. So this double inequality, if I do it like that, I say this is larger than N. But if I put two inequalities, I say much larger. So I'm trying to exaggerate. Okay? So here your time series observations is how much? Is 239. And the number of variables in your X is 44. So in this case, you have that the time series is about 5 times larger than the number of variables. Okay? Which means you have enough degrees of freedom to estimate. And that's why you have the values you have. But in real life, okay, industrial production and monthly setup might be one case, but more importantly, institutions like the Bank of England, like the government, or I don't know, or big hedge funds who follow macro-oriented investment, let's say, strategies, might require to have a forecast for the GDP. So using industrial production, which is monthly, might be okay up to some extent. But what happens if you use GDP, which is quarterly, right? So how many years of data are you going to collect for GDP? 10 years? 15 years? Let's say 15 years. 15 by 4, 15, right? 15 years. By 4, how much? 60. So you will have 60 observations. Okay? 60 observations. And in our case, our X is 44, which means that 60 is still greater than 44. But in practice, remember, you won't have 44, you will have 144, 400 or 1,000 variables, which means that in that setup, your time series will be much smaller than the number of variables. Okay? Let me show you what would happen in that case. It's not the case here, but let's pretend it is. So let's say you want to do this kind of regression. LM to B. Let's use the first 30 observations just to see how things look like. So imagine that you have 1 to 30. You have only 30 time series observations, right? Look what happens. In case the number of time series is much smaller than the number of variables, the dimension of your model, then you don't have enough degrees of freedom to estimate, which means that your standard error, your variances, your t-statistics, your p-values are not defined. And you will find yourself that you have degrees of freedom to estimate up to variable whatever, 21, and after that you cannot estimate anything else. This is called the curse of dimensionality. So the above is an example of the curse of dimensionality. Dimensionality. We might not really have it in this context, because this is just a very simplified example with 44 X's and 240 or 239 time series, but in reality, if you collect data for 300 variables and you have the GDP for 15 years, then 60 is much smaller than 300. So you will have this problem for sure. Okay? So that's the second problem. The first problem is even if you have data is interpretability, and the second problem is if you don't have enough data, or at least when your time series is smaller than the number of x's, because the idea here is to include as many x's as possible. This is problem number 2. The question therefore, how do we solve the above problems when we deal with large number of variables? Okay, to answer this question, we have two approaches, two schools of thought. Now we'll go a bit back at the beginning of our slides. Here is the idea about the curse of dimensionality. Model interpretability, we discussed those things. Now, you have two approaches. One is called variable selection. So one simply says, you cannot use all variables. Fine. Out of these 44 or 400 or 1,000 variables, can I find a methodology that can use this data and tell me that now use variable 1, 5, 15, 24, 35. So can I find a way to select variables? Therefore, variable selection is the idea. And variable selection can be done either by subset selection, therefore model selection, trying out every variable, we will see in a minute, or this can be done by penalized regressions. So here, these terms are all synonymous. Penalized regression, regularization, shrinkage. They all point to the same idea. Okay, so this is still part of variable selection. One approach, therefore, is variable selection. The second approach is called variable reduction, which says you want to find a way to proxy how economy moves. But economy is a very complex thing. You don't observe the economy, you observe variables which come out from the economy. You might say you observe industrial production, you observe prices, you observe, employment. So you have many variables that you observe, right? All these variables, and perhaps even more variables that you cannot think of, consist the economy. And the idea under variable reduction says, try to hug all those variables, and once you take them all together, find a way to summarize. So find a way to extract the information out of all these variables. So under this approach you say, I don't want you to tell me which variables are important, they are all important, but find a way to extract this important information out of all of them. That's variable reduction. The approach of variable reduction. Okay? Questions so far? Is it that clear? Okay, good. File, save as, browse, examples. Okay, now, let's say we have, just to make things a bit easier, let's say we have 3 variables. So we have y, then we have x1, x2, and x3. And we also have our intercept. Okay. In case you have only 3 variables, what are all the possible models that you can consider? OLS. So model 1, you use variable y, that's your, well, let me remove y, y is always there, and then you say, let me use just the intercept. I will not use x1, I will not use x2, I will not use x3. Model 2, let me use the intercept and also x1. Model 3, let me use the intercept and only x2. Model 4, what it is? What is it? Only x3. Model 5, x1 and x2, right? Model 6, x1 and x3 now. Model 7, x2 and x3. Model 8, all. Do you agree? So in this way, aren't we, in some extent, aren't we doing here variable selection? One can say, go to model number 1. Just use an intercept. And once you have this model, once you estimate it, find a statistic that you prefer. For example, one can say Akaike. One can say R squared or adjusted R squared. Another one might say, I will use this model and I will see how this model performs. This is very, very important, be careful. How this model performs in a cross-validation. Do you remember back in week 2 that we discussed about cross-validation? I hope so. So one can say here, model 1, I can do a cross-validation and obtain the mean squared error, a k-fold cross-validation, a leave one out cross-validation. Right? These are just examples. In general, you have a criterion S, a statistic S, whatever you like. The cross-validation mean squared error, the whatever this S can be. And you say model 1, let's say that this S is the leave one out cross-validation mean squared error. Okay, so we can have this kind of understanding. For example, or Akaike or R squared. But Akaike and R squared, they are in sample. They will simply tell you how your model fits. But if you do a cross-validation of this type, will tell you how the model works in parts of your data that you left as out of sample. Okay? So this is now how we start blending together econometrics and machine learning and data analytics, for example. And you go for model 1, and let's say you find that your preferred statistic, let's say the leave one out cross-validation mean squared error is 1.2. Then you go to model 2, and you find that the statistic you have, in this case, is 0.8. And for model 3 is 1.4, for model 4 is 1.6, for model 5 is 1.2 again, for model 6 is 0.67, for model 7 is 1.5, and for model 8 is 3. Okay? Let's say you go model by model, you estimate the models, and you find these values per model. What is the model you choose? If this is a mean squared error in a cross-validation, what is your preferred model here? Any ideas? Louder? Model 6. The one with the smallest value. This is, in case this is a mean squared error, the larger this value, the more error your model. So you're going to choose the one with the smallest error here. Do you agree? That's it. End of story. So now we just did variable selection. We have 3 variables, 3 potential variables, x1, x2, and x3, and for these variables we we used all the possible model combinations. Right? How many models do we have here? 8. So, number of variables, number of models. When your variables are 3, the number of combinations will be 2 in the power of 3. 8. If your variables are 4, how many models will you have? 16. So you will have to do this process for 16 models. If your variables are 5, 32. If your variables are 6, how many combinations? 64. Now they start increasing exponentially. If your variables are 7, 128. If your variables in our case are 40, well, don't go to 44, let's say they are 12. 4,000 models. 15, 32,000 models. 16, 65. You see how it increases. Of course, if you go to 44 we have here, we cannot even write it down, okay? It's a very, very large number of possible models. And of course, imagine that perhaps you have to do that at every point in time. So at every point in time, you say, if I use data up to December 2024, I have to estimate this kind of a bazillion number of models and choose the one with the smallest MSE. In the next month, you have to do it again. The next month, you have to do it again, and so on. Is this feasible? Even in today's terms, with cloud computing and parallel computing and everything, this is still infeasible. It might still be feasible, but you have to wait some weeks, perhaps. You can use an Amazon server, put all those models to run, and wait something like, I don't know, 6 or 7 days for these things, for estimations to finish. Okay? So, this is for 44. Imagine that you're not doing this kind of small exercise we have for our module, but you have something like the Stokes-Watson, 250 variables. Now this becomes infeasible even with today's CPU power. Do you agree that this is not something we can do? So what we can do? This is what we have here. This is called subset selection. This is called an exhaustive search. Okay? Because we are exhaustively trying to find the best combination, taking into account everything. Because this is infeasible, in terms of algorithm, here is what we just did. We say, start with the empty model, the one with just the intercept. Then try to use all the possible combinations by taking k predictors at a time. In our case, k was 1. Okay? Pick the best across these models with a statistic you like. RSS, R squared, mean squared error, whatever you like. And then you keep doing that for every model, okay, until you have finished. So, infeasible. How can we make this feasible now? This is called stepwise selection. It's part of subset, and now it's called stepwise selection. It's called best forward stepwise selection. So, the best forward stepwise selection, so this is what we call exhaustive search. The best forward stepwise selection, best forward selection, BFS, says the following. It says, put your variables in order. We will discuss the order in a minute. X1, X2, and X3. Start with model 1 that has no variables. Calculate the preferred statistic of fit. Whatever you like here. K squared, mean squared error, blah, blah, blah. let's say that the value, let's say we use the mean squared error and the value is 1.2, okay? The next step says model 2 will be what you have in model 1 plus the first variable you have in the right hand side. So this variable and x1 only, okay? Up to this step, it's also what we did in the exhaustive search. You have now the intercept and variable 1. Calculate now the statistic for this model. Let's say this is 0.9. If the statistic of this model, if the fit for this model is better, then this is going to be your adopted model from now on. So if this model improves of what you have, then from now on, model 2 is going to be your choice. If it doesn't improve, so if it is something like 1.4, then you drop it and you go back and you say, no, I will go back to model 1 with just the intercept. Okay, now let's say you keep it. Model 3 will be what you have in your adopted model 1.1 plus the variable which is next in line, x2. Which means if I include x2 in my currently working model, can I get something better? And let's say that here this is 1.05. Now you see that by including x2, your fit worsens compared to what you had without x2. Therefore, what is your choice? Here you choose obviously model 1, you have nothing to choose. Here you choose model 2, and here again you choose model 2. You say no, by including x1 that I had plus 1 new, the x2, doesn't work. So I prefer to go back to model 2. Then you go model 4, which is what you have currently, so model 2, this you have tried doesn't work, plus the variable next to it. Okay? And now you say this is, I don't know, 0.85. So now this improves of your current working model. So now you adopt model 4 from now on. Okay? So think of it that you put your variables in order and you say variable 1, put in the model, works, keep it. Variable 2, put it, works, no, drop it. Variable 3, works, keep it. Variable 4, works, keep it. Right? Variable 5, works, no, drop it. So in this way you start going variable by variable, and what works you keep it, and what doesn't work you drop it. However, in order to reduce the number of estimations, unfortunately, what works in the way your variables enter your model, what works you have to keep it. So if variable 1 works, as you can see here, we kept it and we kept carrying variable 1 for all other cases. We tried variable 2 didn't work, we dropped it. We kept variable 3 worked, and now we have to carry from now on variable 1 and variable 3. Okay? And keeps going in this way. This is called best forward stepwise selection, because simply we start from a model with no variables and we go forward by adding more and more variables. Questions so far? A big question is how you order the variables, because one can say in this case here you simply put, I don't know, trade exports, trade imports, production construction, but why should I use this order? Perhaps before starting doing the exhaustive search, perhaps the idea would be to do a first step, which is first try to put the variables in such a way so that variables which are more likely to affect your y go first. What are the variables more likely to affect y? How can I identify them? I would say in the simplest case of all, correlation. So I would try to take correlation of y with every variable, and I would put here the variable with first, with the largest correlation in absolute. I don't care if it is minus 0.8 or 0.8. I care for the correlation to be very large, either positive or negative. So perhaps one idea would be to place the variables in such an order so that they are the most correlated first. Another idea would be to take, which is a bit more complicated, would be to take every variable separately and do a sort of case of out of sum cross validation. So take model 1 with x1, do the cross validation only with this variable. Model 1 with x2, only with this variable, and then order the variables according to the smallest mean squared error, if you want to have an out of sum flavor in this idea. Therefore, this is called the best forward stepwise selection. Okay? There is also the best backward selection. The best backward selection, it is the same idea, but instead of starting with the empty model, the one with no variables, you start with the full model, the one where you have all the variables, and once you have all the variables there, you say, but if I drop variable 1, is it better? If I drop variable 2, is it better? So it's the same process, but from a reverse side. Now, this is not feasible in our case, because if you want to estimate the full model, okay, the full model, in case we collect many variables, will suffer from the curse of dimensionality. Okay, so the idea here is to avoid having to estimate a full model. Because if we're about to estimate the full model, okay, perhaps there is no reason of dealing with all these things. The idea is that we cannot estimate the full model, we cannot interpret the full model in a nice way, even if when we can estimate it. So we want to find another approach. Okay, so the best backward selection is infeasible for economics, I would say. So this ends up with exhaustive search. In case it's feasible, it's not. Computationally in this case, and this leaves you only with the best forward subset selection. So let's see that in R. We will not use it in the module, but it's a good first step into the variable selection approach. You have to load libraries. So library Ellipse. There is a library called Ellipse, and this library does stepwise selection, either forward or backward. So forward, what we just discussed, backward, we just discussed, data we discussed, seasonalities we discussed, all these things we have discussed them. Okay, and now the example. Where's the example? Here. Okay, so you have a y and an x. I will simply copy and paste what you have here. No. Or what we have in the code. Which is here. There we are. So here we say, what is your x? Our x is the 44 variables. What is your y? The y is the variable we have, the y. N best, this is on the slides, is k, how many variables at a time. And nv max to be all the variables. Intercept true, method forward. Okay, now by doing this, which is done, let us try to see the output. If we do summary, yes. So this, look, it's very important. this tells you okay, HD2, it starts with HD2, tries HD2. It works, so it keeps it. Then it is not, here we have, it uses the ordering that we provided, but the algorithm is not using this ordering. It tries HD2 first, but then goes to HD4, which is the next most correlated variable, and then keeps it. Then goes to HD3, which is the third most correlated variable. Then goes to SD3, which is the fourth most correlated variable. This is why you have this output. The algorithm will not go on variable by variable in the way we provide them, but first we'll rank them according to correlation, and then we'll try them out in the same way we discussed. Okay? And here you can see how it goes at variable by variable and so on, how it tries them out. This is not the full output, as you can see here. Now, the question is, out of all these forward models, what is the one that you choose? And now you have your criterion. Are you going to choose the model with the largest R squared? Wrong. What do you see in the left-hand side? Exactly what you know. What do you know? That the R squared, by construction, by definition, the larger the number of variables, the larger the dimension of your model, the higher the R squared. And that's evident here. So this is now, it's a visual illustration why the R squared is not good for model selection. Because it suffers, and by the more variables you include, the larger the R squared. Of course, it will go and tell you choose the one with 44 variables. Wrong. The adjusted, look how it works. It increases up to a point, but after that, so it tells you use about 15 variables. Not necessarily the first 15 variables, but some 15 out of the 44. So it says use some 15 variables. We will see which ones. And after that, the more variables you include, it starts falling. You don't trust the adjusted R squared. Try to use Akaike or Bayesian, if you prefer. Okay, so you want to choose the model with the number of variables with the smallest Akaike, which is somewhere here, about 14, 13 or something. And you know that Akaike usually allows, it's a bit more relaxed in terms of penalty, so it allows more variables to enter. Bayesian is stricter, and it only tells you use about 6 variables. Okay? I am not sure if the code can do cross-validation here. I can't really remember. So let's see. What are these variables? Let's use the adjusted R squared and the Akaike and the Bayesian. And let's see what kind of similarities we have. So R squared says use the intercept and then use HD3, HD2, 3, 4, 5, 9, SD1, 3, 8, and so on. Okay, that's adjusted R squared. Akaike says use these variables. There is some sort of similarity I can see. And Bayesian, which is the most, let's say, strict one, says only use these 7 variables. HD 2, 3, 4, and some SD3, 8, and 33. So this is actually what we have done here. We just did model variable selection. And the answer, of course, changes depending on our preference. It changes depending on the criterion we use. It changes depending on how strict is this criterion and so on. Therefore, how do we choose? Unfortunately, the answer to this question, so up to this question we say, let's try it out. How do we finally choose the criterion? You have to do a separate cross-validation analysis, and you have to say, Do I want to do forecasting? You have to write an out-of-sample cross-validation forecasting exercise and say, how does forecasting work when I use the variables chosen by the adjusted squared? How does it work when I use the variables chosen by Akaike? How does it work when I use the variables chosen by Bayesian? And then you will have the evidence you are looking for. Okay? So this is not done. We cannot stop here because we haven't answered to somebody in case which criterion are you going to choose. And you have now to take more actions. But this is the first step, let's say. Best subset selection. What is, now before we go to break, I told you earlier that this is a method we are not going to use. What are, for every methodology we have today and next week, we have advantages and disadvantages. Very important. Advantages of best subset selection. Easy to use, easy to interpret, right? It can handle any number of variables. The best forward subset selection, if you input 44 or 400 or 1000, it will start trying out the variables and give you, what works, what doesn't. So it doesn't suffer from the case of dimensionality. These are the advantages. Disadvantage now. The most important disadvantage is that this methodology does not take into account the full information in the cross-section. Now, what does cross-section mean? Okay, so cross-section means when we have a data set like this one, you have information vertically. So you have information across time, HD1, HD2 across time, HD3 across time. The weights variable varies across time. This is information, right? Variability. Do you agree? Now, you have information vertically, but you also have information horizontally. A value from 0.54 to 0.87 to minus 357 to minus 0.1 to minus 0.07. So when you look at your data vertically, you also have information. And this information is when you combine these variables, therefore cross-section of these variables. So time information and cross-section information. Now, why did I say that the subset selection is not using, so perhaps with red, is not using the full information? It uses part of it. Why? Look here. You start with the empty model, the one with no variables, just the intercept. And then you say, the intercept and variable 1 works, keep it. And then you say, the intercept, variable 1 and 2 together, so now you start using the time information and the cross-section between x1 and x2. And you see that x1, when combined with x2, or in a reverse way, x2, when combined with the existing x1, do not really work nicely together. This might be due to the fact that x2 independently is not a good variable, is not a good predictor for y, or it might be due to the fact that x1 and x2 simply they are not a good match, let's put it simply. Okay? They don't have useful cross-sectional information. And therefore now you say, drop it. Since x1 and x2 don't work well together, drop x2 and go here. And then try x3. And what you find here with x3, that if you use x1 and x3 together, with the time information and the cross-section information, now you have something better than what you had before. So you keep it, right? But who says that in case you could use x2, which was dropped in the previous step, and x3, these two variables together are not better than x1? So do you see my point? My point is that by simply going forward, because you have this computational burden, and you cannot do another way. You have to go in a forward way and try out variables. And what works, you keep it, and what doesn't, you drop it. But this has a cost. And the cost is that the variable you drop earlier, x2, with a variable which comes later, x2 with x45, you will never have the chance to use these variables in a combination in this approach. So you solve a problem of dimensionality, you solve a problem of estimation, but you have another problem which is the information in the cross-section. So you sacrifice some information of the cross-section to get something which is easily done. Okay? That's the disadvantage of the method. So, break, and then we come back and see how we solve it. 10:21, so we come back at 10:35. Good? 14 minutes break. Hi Charles, just 1 second, you should come here. Okay. Yeah.
A very simple question. Out of the 3 projects, the optional one, which is the hardest, do we get more points for doing that one?
No.
So, okay.
No, because I haven't mentioned that from day one.
Okay.
So no.
Yeah, because it sounded interesting.
It is.
My also project too, so.
Okay.
So, yeah, thank you.
Hello. How are you?
Good. How are you?
I'm good, thanks.
I have a problem with our lecture. So last time you say for example one, each group have to find the variables match the people in the group, right?
Yeah.
So how about you take the
Same thing.
same thing?
Same workload.
Okay, I see.
Yeah.
So and about the variables, I've tried some variables, but somehow I find some variables don't have the system problems. So it's okay for our project, or it's just I don't know,
So
express.
what is the project? 1 or 2?
Two.
2. Forecasting. And what are the variables you're thinking?
WTI.
WTI.
Petroleum.
But this is just one variable.
Yeah. So,
Perhaps you can use WTI, gold, Bitcoin, I don't know. Bitcoin, don't use it, it's very strange, don't use Bitcoin. But you can try to find variables which are closer related to for example, you say Brent crude oil related variables, I would say. Try to do something like that. Factors moving Brent crude prices, you see? So perhaps You can go and do. How many are you in your group? How many people?
5.
5.
Yeah.
So I would say if crude oil is one of factors, what are the factors here? So if crude oil is one, let's say, variable, another variable could be, no, I don't like this, the futures, forecasting the normal oil prices now. So I would say data. Variables. Hold on. Variables. Okay. So they say, for example, you could have a measure of global real economic activity, crude oil inventories. Perhaps this is too much. Perhaps it's too much. I would do something like, I would do something like Brent crude oil. I would do something like US industrial production. I would do something like US consumer price index, which they have some sort of relationship.
Yeah.
I would also do something like what else?
Another
Crude oil predictors. What are they using here? So if you do this kind of Google search, you will find variables, which also make sense, right? So US national production, US CPI, crude oil, crude oil, price factors, they say here. So here they say you have to find something about demand, something about supply, something about inventory, something about financial market. So macroeconomy, we have it. Is this and this. WTI, we have it. Financial market, you can do something like US S&P 500 return. These are policy uncertainty. So you can also use this. It's a free data for the USA. It's here. This is called US Economic Policy Uncertainty. What is your email address? This one?
Yeah.
Possible variables. How many are you? 5?
5.
5. Okay. So we have WTI, and for here you have to use the log return. That's your stationary thing.
Yeah, log return is stationary.
Log return. Here you have to use the log growth. Here you have to use the log growth. Here you have to use the log return. And here you can take the first difference. And this one variable is here. You click download data and you will get the data.
Okay.
Good? So you have your variables.
Okay.
Nice?
Nice.
And of course, in your case, you do individual variable forecasting. And perhaps you can say that from 2020 to 2024, it is harder to forecast WTI, it is easier to forecast S&P, it is harder to forecast CPI, whatever you like. Or you can simply, I don't know, it's up to you
Okay.
what you want to do.
Okay.
Okay, but these are some variables about the Brent crude oil.
Thank you.
Good. Yes.
So for the project, we were thinking of using the Brent crude oil prices to study the global.
Yeah, be careful with this huge drop there, okay?
Yeah. So the question I have is there a package to download this data for R, or do I have to manually?
From the Federal Reserve Bank of St. Louis?
Yeah.
I think there is.
Because I tried googling it and I couldn't find. It says from Yahoo Finance. So I wasn't sure.
I think there is. I'm not sure if it still works, but I think there is. It's called Fred Data in R. It's called Fred R.
Right now, that's it.
Yeah.
And then and the purpose of
You need. You have to follow those steps. You need to do it to find an API and these kind of things. I haven't used it,
oh, okay.
but there is a package, and you can find this vignette, and you can see step by step how it's done. Okay. You have to use this kind of API, but you have to follow those steps so you can get a key. You can get a key like that.
From Friday.
Yeah, it says to use Fredar, you go here, you obtain a Fred API key, and then you start your code and you use it here.
And then, so after the variables, I will be selecting 4 countries and then comparing the effect on global prices.
4 countries, about what?
Supply and demand of crude oil.
Okay, for US it's easy. How about the other countries?
Saudi, they produce.
Have you found data? Because I'm not sure if you can find, check, I'm not sure if you can find the data there. Or how easy it is to find the data.
Saudi, then Russia, and India.
Okay, it sounds okay, as long as you can find data. Because Fred is easy. But the others, is on Bloomberg, is it on Reuters? I don't know, you have to check. Yeah? You're in the same group? Yes? Yes?
I have one question. In the code, especially in last seminar, so that we can use AIC or PIC to find out which lag is the optimal lag to use.
Oh yes, for the crisis.
Yeah.
Yes, yeah.
My issue is I can modify the lag 0, 1 to get the desirable result that I want, but the purpose of the test is to know what's the best lag.
Yes, but the idea is that, you have a test and you want with this test to say something about now. It's not a forecasting methodology. It's a methodology that you put your data and the methodology says, right now you start having a bubble or you start having a crisis. Now, in order for the test to work now, you have to match the way the test works with all your past events. So, by playing around with a number of lags, or with Akaike, Akaike might not always show you the best match. Even though in theory it's supposed to do, it is just a test, it's not an economist. So you can try Akaike, I think we have it as an option, or not. No. I'm not sure if the package has it, let me check. Exuber in R. Let me check if there is an option. Exuber. It's the RADF or the GS. What is the function we use there? RADF.
ADF, so we use the extra,
Yeah.
like the last year, to get the ADF. But because I've already assigned the last one, right? So I want to know how can I tell which lab is the
But this
best.
is not the code I used last week.
This is in the webinar.
Correct, but in the webinar, this PSY, RADF, good, RADF, which goes here. Yeah. I do think it has it, let me check again. No, it doesn't have it. No, it doesn't have it, unfortunately. So, the package, I mean, they're different ADF like ADF lab. Find the isolate Z and you put we stopped with the disadvantage of. You can also say, guys, be careful, the bubble might be approaching. Of course now you know that there is no bubble because the rest of the data came. But if you isolate only this part of the data, you will see that the test thinks there is a bubble when it is not, simply because there is this huge increase compared to the recent past. And here the same thing. And here the same thing, it starts falling down, it's about to have a crisis because now you have a value which is smaller than the previous past. And here as well.
This is how I can alternate.
Yes.
I don't like it.
No, since we don't have a methodology, the framework, that's fine. What we just discussed is perfectly acceptable.
Thank you very much.
You're welcome. Okay guys, we are back. Let's take our seats and let's continue. So, before the break, we stopped with the disadvantage of the subset selection. And then we ask ourselves, but how can we solve this problem? How can we have a very big data set, like this one here, that we can solve two problems at the same time? Problem number one, to use all the data without suffering from the curse of dimensionality. Problem number two, again to use all this data so we don't lose information from the cross section. The answer to this question is called regularization, it's called shrinkage, which is here. So, statistically speaking, we say regularization. Regularization in terms of matrix algebra is when you have a matrix and another matrix and you take a linear combination. So, I will try to explain this in very simple terms since we don't do matrix algebra here. Okay? And I will say the following. You have a matrix X. Do you know what? When we call a matrix invertible, do you know what this is? It's called matrix algebra. An X matrix is invertible if you can take the X in the power of -1. That's the invert. Okay? Now, you might have a matrix X which is non-invertible. But when you take a combination of X and another matrix Z and you put them together, alpha x plus beta z or x plus beta z and you put them together, you end up with another matrix, okay, the sum of these two matrices, which now is invertible. So it is a trick. And this is why we call that when you have a matrix X, another matrix Z, you shrink, you target matrix X towards matrix Z. So you have another new matrix which solves this problem. This is why we call it regularization and what regularization is in statistics. Now, in econometrics, we go back to this setup. We go back to our OLS. Why OLS? Because OLS takes into account your information at the cross-section when you put all your variables. So this is, what is this actually? Shh. You go to the exams and somebody gives you this slide and says comment. What do you see? Without the text, just the equations. Okay, it says, please explain what is this. What is it? The OLS estimator, right? And it says, if I have a y and some x's, here the x's are in matrix format, so you have x1, x2, x3, x4, you have p x's, okay? And you have n observations. It says that to find beta hat, you have to find the values for beta that minimize the residual sum of squares, right? This is part from our first module. It says, if you go back to 7QQMO 1, not 101, but 811, yes, you will find the same formulas. And RSS is defined as this equation where you first sum across variables beta 1 x1 plus beta 2 x2 plus beta 3 x3. You take the difference from your y, so you have your residual, your estimate of your error. You put this square, so you have the squared error, and you sum across your time observations. Therefore, you have the sum, the residual sum of squares in this way. Okay. If I want to write the same expression here in matrix format, so this is the expression using the sum operator. If I want to write the same expression in matrix format, I can write it in this way. Beta hat is x prime x in the power of -1, so x prime x inverse, multiplied by x prime y. Okay, this is how you can write this in matrix format. Now, if you go in this matrix format, you will see that there is a matrix which is about to be inverted. It is this x prime x inverse. This x prime x inverse, x prime x, is actually your variance covariance matrix of your x's. Okay? So, the beta takes, therefore, OLS takes into account the variance covariance matrix, which is what you have here. Now, this is the standard OLS, which, as we said, doesn't work if you have a large number of variables. If you have a large number of variables, this x prime x inverse is non-invertible. Okay? Therefore, what we say, the curse of dimensionality. It makes this x prime x inverse matrix to be non-invertible. It makes this not to have enough degrees of freedom to estimate. It's exactly the same concept. One from the sum perspective, one from the matrix perspective, matrix algebra perspective. And then we say, but if the OLS as is doesn't work, can we find something else, something close to it? Can we combine the OLS and add something more, another term here, so that if this doesn't work, we can trick it and this whole thing works. So this is called now a regularization. This is called shrinkage. This is called penalized regression. because you take the regression you have and you add this thing, this whole thing together, which is highlighted here in blue, here, is called the penalty term. So now this says, take this OLS, which by definition is a sum of squares, right? Sum of squares. If I have -1, what is the square of -1? 1. So negative values become positive, correct? If I have 0, what is the square of 0? 0, which means that in the square, when you take the square of something, negative values become positive and zeros remain zeros. So therefore, by definition, this whole thing is non-negative. It can be 0 and above. Do you agree? It's a square, it's a sum of squares. Right. And then we say, and this is the solution of OLS. So imagine that here I hold a little ball, and this ball is the solution of OLS, this bubble. Let's say I have a little bubble here. Now, for given variables, you have a solution. This is what we call equilibrium, okay? You have a function and you find the optimal of this function for some data, for some variables. Now, what we say that this doesn't exist. This doesn't really work. So we say, let's try to take what we have and try to add this term. Let's take a very good look at this term here. This is plus lambda multiplied by sigma, so this is the sum from 1 to p of vitas. Not just vitas, but vita squared, which means that again, this part is non-negative. And we say, this lambda, called the tuning parameter, I define it, okay, to be greater or equal to 0. Obviously, if lambda is equal to 0, what happens to this whole term? It vanishes. So, this, if lambda is 0, this term vanishes, and what I have is just the OLS. But if lambda is even slightly above 0, then I have the OLS function and the solution, but now the OLS function has increased, is inflated. So if here I have the OLS and the solution, by inflating the function, since everything is in squares, everything is non-negative, by increasing the function in order to have equilibrium, what happens to my solution? If the function goes up, the solution goes down. Okay? And I have vita in squared here, vita in squared here. So therefore, to have a solution in my inflated function, I am pushing the vita squares down. So I'm pushing the optimal values for these vita squares to go down. Okay? This is called penalized regression, and this is called Ridge. This is the Ridge regression formula. Up to this point, this is part of machine learning. And now you will ask me, why machine learning? This is just OLS. It is OLS. And machine learning now kicks in to answer the question, how do we choose lambda? So, should we use lambda? There is no theory for lambda. It is just a trick. It is a technical trick and says you cannot find a solution to this function. Try that function. Okay? So if you cannot find the vitas that minimize this, try to find the vitas that minimize this whole thing. Vita in this term, vita also in this term. It's not a constant. If I add a constant, it will not work. I have to add a quantity to be minimized as well. So I need to have vita in the first term and vita in the second term. What vita? I have to say vita squared for two reasons. Since this is squared, to match my first term, and also to make sure that this is non-negative. So by including this term, will only push my function up, and therefore push my solution down. Okay? Now, the question of course is, since there is no theory, it's just a technical trick, what is the value for lambda? And do we have a single value for lambda? Or does this change from case to case, from case study to case study? Or does this depend on our data? And of course the answer is the latter. It depends on our data. So every time we have to choose to assign a value to an unknown parameter that we have no idea how to do it, machine learning and data analytics come in to help us, and we use cross-validation, which is what we discussed weeks ago. And here you have a parameter lambda, which is unknown, and you say, how do I choose this parameter? And the answer is very simple, right? I go here and I say, ridge regression, lambda. You will do a sort of cross-validation, a grid search cross-validation. So you will say potential lambda values, right? And you can say, when lambda is 0, I have OLS, but if I have so many variables, OLS is not defined. So perhaps I can go 0.05, something very close to 0. So by having this kind of lambda, this is lambda 1, let's say, right? I can come here and say, find the solution to this function, which is plus 0.05. And this, I will press the button, and this will give me some vitas. Will tell me vita 1, 1.3, vita 2, 1.4, vita 3, minus 1.5. So this now will have a solution. And therefore, here I will have a value for vita 1, blah, 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 value for vita 2, blah, 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 value for vita p, if I have p variables, blah, blah, blah. So by using a very small number of lambda, I will get a solution. Is this solution good? I don't know, so I will do a cross-validation, and I will say, for this lambda, I will do a leave one out cross-validation and find that the mean squared error is this, 0.8. Then I will use another lambda, slightly more, 0.01 for example, sorry, 0.1. Or of course you can go 0.05, 0.06, you can go 0.05, 0.1. So the step that you will change your lambda, there is no theory, there is no rule, it depends on you. You can do something like that. Okay? You can do larger steps. You can do 0.1, 0.2, 0.3, 0.4. You can do 0.05, 1, 2, 3. So there is no rule on the step of the potential lambda values. And of course, you can keep doing that until you have, I don't know, a very, very large lambda. So I say here, a very large lambda. Okay? But the point is that for every possible value of lambda, this is called a grid search. We're trying to find out of many potential values, we're trying to find the value which works best. So the value that gives us the vitas that have the smallest mean squared error in a cross-validation. 0.5, mean squared error 3, 1.4, mean squared error 4, 1.6, and so on. So if these are the choices we have, we will say, for this data, for this period I analyze, I will choose the lambda that, when I plug it in this equation, provides me with the vita estimates that give me the best fit. Say it's here, for example. Okay? By changing now dataset, you have to redo everything. And you have to do this again. And it might give you another lambda. And for another country, for another dataset, another lambda, and you keep doing that. So this is the way that one can choose the value for lambda in this ridge regression, in this penalized regression. It is that simple. But of course, in this setup, which is not an OLS, p-values, t-statistics are not defined, do not exist. And if t-statistics do not exist, p-values do not exist. So you cannot really say which variable is statistically significant or not. We don't have statistical significance in this setup. And of course you will ask me, how do you choose variables? There is no answer. The answer is subjective. It depends on you. We'll see in a minute. But since there are no p-values, there are no t-statistics, we cannot do inference here in this setup. We have to find a way so that the resulting coefficient estimates for β1, β2, β3 are comparable to each other. What you have here is not comparable. Look. So this will be code number 2. File save as code number 2. Are your vitas comparable? To be comparable, you need your variables to be also comparable. Okay, what do I mean by that? Look here. Summary lm y tilde. Let's say I will take variable, one with tiny values, hd6, one with very big values. Anything in tens, perhaps SD1. So let's try to take these two variables, hd6, SD1. hd6, SD1. Still not ideal. Let me find another case. HD5, SD. Okay, this one. So, let's say you have this estimation output. Let's say that these variables are these coefficients are statistically significant, and you say alpha hat 0.05, beta 1 hat minus 0.33, beta 2 hat 0.05. Can you argue that this variable, the first variable, has more impact, negative impact in that case, compared to that variable? So somebody, let's say that these are both significant, and somebody would say, can I say that the variable with the largest coefficient in magnitude has more impact on my y? What do you think? As it is, this is wrong, because the vitas in the OLS reflect the change in the level. So variables which have very small values, like HD5 here, not 6, but 5. So you see, a variable which has very small values, 0, 1, 0, 0, minus 0, 1, 0, 0, will take a larger coefficient in magnitude, not the sign, but in magnitude. And variables which have very large values, compared to y, like SD1, are going to take smaller coefficients, so that this adjusts the level differences between your x1 and x2 compared to your y. Okay? So as it is, we cannot argue that variable 5 has a larger impact, simply because we have a larger coefficient in scale, because HD5 is much smaller in terms of scale compared to our y. Therefore, these variables are not comparable, and therefore their coefficient estimates are not comparable. How can we make them comparable? We have to do what is called standardization. Standardization. Let's say you have these three variables, I would say, only for this data. Okay? These variables are measured in different scales. Where are the cells? Here. Okay? What is the sample mean? What is the sample standard deviation? Let's look. Average. Standard deviation. So, you will see that they have different means, 0.7, 0.36, 0.36, perhaps these two are a bit closer to be comparable, and they also have very different standard deviations. Therefore, this tells us that these variables cannot be compared. How can we standardize them? So, HD2 standardized, HD3 standardized, HD4 standardized. To standardize variables, we have to make sure that they are expressed in the same way, which means they have the same mean and the same variance. And how do we do that? We can subtract from each variable its own mean. So from HD2, subtract the average. This is called centering. And by dividing with the standard deviation, this is called scaling. You have to center them and then you have to scale them. And you do that for each variable with its own mean and standard deviation, and therefore you are transforming your variables into some new versions of them, which now, what happens with these variables? Let's look. They have the same mean, 0, and they have the same variance. Format number 3. Okay? Look, they have exactly the same mean and exactly the same variance. Are they equal? No. They are just expressed in the same way, in the same scale. Okay? Which means that HD2 now is comparable to HD3. And now you will ask me, but is this the same variable? Let's look. Let's go to HD2 and make this plot. Okay? So the blue line is your original series. The orange line is your standardized series. And obviously you can see that now the level has dropped. And of course you will see that the orange line is above and below 0. Its mean. Now, in econometrics, what is information? Information is not where your variable varies, but it is that your variable varies. So, information is your variable goes up and down. It doesn't stay constant. If it is constant, it's not a variable. So the idea is that it goes up and down. It doesn't matter if it is up and down above and below 0, or above and below 5, or above and below 6. So the point that varies doesn't matter. Now, let's look. It matters the way that the line moves here, the way the variable moves. So, let me now plot, because I cannot actually compare the blue and the orange. They are expressed in different scales. Blue line, my original variable, in the original scale. Orange line, the standardized version of that variable, in the 0 scale. Now, 0 level. Now, let me plot this in a different axis, and look very closely what is going to happen. Okay, ready? If you actually make the plot in different axes so that the two lines are expressed on the appropriate axis, you will see that the two lines are almost identical. So the way that your original variable goes up and down is exactly the same way or very similar to the way that your new standardized variable goes up and down. So standardization does not mean that you lose information. Standardization only means that the information that you have across variables can be comparable. Okay? Another thing you can do is that if you make a plot of your original HD2, 3 and 4, you will see that they're a bit distinct to each other. But if you make a plot of the standardized versions of this variable, you will see that since they're expressed in the same way, they are closer to each other, in case this is evident. I don't think it's that evident, but anyway. Okay? So this is the most important thing. Therefore, in ridge regression, we have to standardize our variables to make sure that the vitas are comparable. It doesn't matter if?
When you're doing the standardization, it doesn't matter if your distribution is not normal.
What distribution of the variables? Distribution doesn't matter. It matters, we do the standardization so that when the data enters this function, we can have the appropriate optimal. So we can have the correct values of vita, which incomparable one to another will give you the correct output. So this is only used to enter this optimization function. We don't care about distributions here. We assume normality, even if it is not always there. This is when you assume Gaussianity, when you assume normality.
But if you're standardizing the variable and it's like, say, outliers with this skew.
We don't, yes, so we assume that they are all normal, but in a with a different mean and variance. And by adjusting them with this way, you are making it their own normal with the same mean and variance. Yeah? If you want to talk about distribution. So what we have here, it is indeed when you have normality. But in practice, you have to check if you have normality or not. Even in any case, we don't check it, we just go and assume that it is there. Okay? In our case, remember, we did our best to make sure that there are no outliers, no seasonalities, no problems, no potential factors that will mess our distribution. So most of the times, when you take good care of cleaning your data, it will come up as normal. So we discussed about standardization. We discussed about cross-validation for lambda. Okay? You can use K tenfold or leave one out, which is my preferred method, as we discussed weeks ago. Please go back to your slides and your notes. We discussed about standardization, and let's see now the example. So we now need to use the package glmnet. glmnet. Use ridge. Okay? Now, what is the first step? The first step is that we don't know the value for lambda. So we need to do a cross-validation. Cross-validation, CV. So we're going to use the function which is called CV. So out to be cv.glmnet. Okay? X to be the capital X, Y to be the big Y. N folds. Do you want to do 10-fold cross-validation? So do you want to come here and say, I will take this value for lambda and I will do a 10-fold cross-validation? If yes, you simply put 10 here in the number of folds. So use reads cv.glmnet does the cross-validation for lambda. N folds is the number of k folds as we discussed weeks ago. Okay? If n folds is equal to your sample size, then you're not doing k fold anymore, but you do the algorithm, leave one out. So if I change this from 10 or 5 or whatever folds you think is best to n row of x or y, then here I am setting to use the leave one out, which is what I prefer. More settings. More settings is about your alpha. Standardize. Is your data standardized? If it is, say this false. If it is not and you want the function to standardize your variables, say true. And then the other thing we have to add here is this alpha. So GLMNet in general has a parameter called alpha. This is not the intercept. The intercept is actually is called intercept. And you say, do you want an intercept? True. This alpha here is an indicator variable and says to choose the methodology. When alpha is 0, then you do ridge regression. When alpha is 1, you do lasso that we'll see in a minute. So by making this alpha 0, we do ridge, and you can simply run this. Out.r, I will call it to have the same here. Out.r. You wait for the cross-validation, it's done, okay? And now you will ask me, let's go step by step. You will ask me, wait a minute, in the Excel file, you showed to us that there is a number of potential lambda values. What are the lambda values that this function has used? You haven't specified them. True. If I want to specify them, I have to go here, cv.glmnet. I have to go in this function and further add this lambda. So I can go here and say, for lambda, use 0.05, 0.15, and so on, if I want to specify myself. Or I can leave the function to determine what are some possible potential values for lambda. And that's what we have done here. So what are the values of lambda that the function considers? Okay, out r lambda. So this function starts from lambda 0.05698, goes to 0062, 0068, 0075, goes, blah, 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 all the way up to 569, okay? So these values, it starts from 005, 006, 007, and goes all the way to 569. You can see here, this is done automatically based on some characteristics of our data. If you don't like what the function does automatically, you can supply your own lambda sequence. Okay? Then, what is the best value of lambda? So, after this kind of cross-validation, what is the value of lambda that we can finally choose? So, what is the value of lambda that gives us the vitas that in the leave one out cross validation have the smallest mean squared error? Oh, this is wrong. In this example, it will be this case, the smallest mean squared error. So we go lambda min, and this will be, it will not be the one very close to OLS, not the one the 0056, it will be the one which is 0.909287 0.67. So it will be this value of lambda. Okay? And for this lambda, So this will be lambda r. And for this lambda, before that, well, for this lambda, what are the corresponding vita hat, the coefficients? So we do coef out dot r, comma, lambda dot r. Lambda here. And this tells us and says, it's here. For this lambda, the coefficients which give you the smallest mean squared error are those. This alpha hat, this beta 1 hat, no p-values, okay? No t-tests, okay? How about all lambdas? You can make a plot of this out.r. Now, what do we see in this plot? Okay, very important. If you look very closely in the horizontal axis, it says log of lambda. It doesn't say lambda, it says log of lambda. This is only done for the figure, so that it can spread out the values and show this nice, let's say, shape. Okay, what we are actually using is the one that I showed you earlier. These are the actual values for lambda, no logs. Only in the plot you take the log of these values to spread it out and make the output a bit more visible. So what you have horizontally, therefore, the log of lambda, so you have the different values of lambda. And when the lambda is very, very small, very close to LS, you have this mean squared error in your cross-validation, about 2.1. As you start increasing lambda, so as you now starting pushing your function to go up, to inflate, right? You can see that the mean squared error starts dropping up to a point somewhere here, which is where our lambda mean is, the 0.92. And then, as you keep increasing lambda, it doesn't work anymore, and the error in the cross-validation starts increasing. So this is the answer. What lambda is the best? Well, the best lambda is the one that gives me, in a cross-validation, the coefficients with the smallest mean squared error. Mean squared error is on the vertical axis, lambda on the horizontal, where you have the minimum in the choice of lambda here, 0.92. The top horizontal axis, 44, 44, 44, 44, everywhere. Okay? So this tells us that for every lambda, the optimization function gives us coefficients for 44 variables. Nothing is zero. Okay? Which means that the ridge regression solves the problem of dimensionality. It can give you vitas, solves the problem of cross-sectional, because you include all variables at one go, but does not do variable selection. It simply says you have to use all 44 variables. Let's look at the coefficients a bit. So in this plot, now, vertically, you don't have the mean squared error anymore, but you have the values for your vitas. Every line, here you have 44 lines for 44 variables, 44 vitas. This is the vita for variable 4. When lambda is very small, it's very close to 0, this coefficient for variable 4 is minus 1.6. As lambda increases, this coefficient, negative, is being pushed to 0. And from the other side, the positive coefficients are also pushed down to 0. which actually this plot shows to you the effect of penalization. The larger the penalty, the more you push your solution down. But your solution in the function is squared. Therefore, you push the squares down to 0, which means negative values are being pushed to 0, positive values are being pushed down to 0. Do you see? Of course, and after a point, they are very, very close, never equal to 0, but always very close to 0 as you go in very, very, very large penalties. Okay? Where is the optimal solution? To the vertical line. This is the lambda 0.92. So this is the best vita for variable 4, the best vita for variable 30, the best vita for variable 9, the best vita for variable 5, and so on. Okay? That's the idea behind ridge. Of course, we can export the ridge solution, export and comment on the ridge solution. Write.csv ridge.csv. This is beta ridge as matrix. This is code 2.24. Okay, here we are. Let's look at the vitas.